is very important for the beginners. So first of all, we'll take a simple example of a simply supported beam. So let us, it is equals to 6 meter span, and it is subjected to the UDL of 20 kilonewton per meter. So we'll create a model by using a ready-made template. So here, this is the template for the beam. So before to start to create a model, first of all, check the unit. So let us keep our unit as a kilonewton, load in kilonewton, distance in meter, and temperature in degree centigrade. Okay, so then select a beam model. Okay, so number of span for the case, first case we'll take as the single span beam, and the span length equals to 6 meter. Now here, in this case, so this is here we have to fill the information regarding the beam properties, the beam material property and beam dimension property. But in this tutorial, this is not important to us right now. So therefore, we'll keep the default value as it is. Okay, so these are the two windows. So the two windows are not required for a simple model. Okay, now this is a simply supported beam of a span equal to 6 meter. So it is a, so in this way, so using a template, easily we can create a model. Then we'll apply a load of a 20 kilonewton per meter on this beam as a UDL. So we'll call this load as the wall load. Now, first of all, define the loading. First of all, define the loading. The procedure is like this. After creation of the model, define the load, then assign the load, and then analysis, then see the analysis result. And if the design part is there, then after that, do the design. So this will be the procedure for all types of the model, all types of the structures. So here, first of all, define the loading. So for definition of the load, only this is the command. Okay, so it is a load pattern. Define the load pattern. Then one table comes. Okay, so in this, what are the different loads to be applied on the model? So just make a list of this. Okay, so in this particular case, we will develop only, we'll create only a simple, only one load case, load pattern, that is a wall load. It is a wall load. What is the type of the load? Okay, so it is not a dead load. Dead load in the sense self-weight of the structure, it is called as a dead load. Self-weight of the structure, it is called as a dead load. So in SAP 2000, we remember that in SAP 2000, dead load software automatically creates. So it automatically assigns the dead loads. So the user need not necessarily to define separately the dead load. And apart from this dead load, what are the other loads are there? So that is maybe a wall load, live load, snow load. Okay, so like this. So these loads we have to define in this table separately. And for all the loads other than dead load, self-weight multiplier should be equal to 0. That means we have to define them. It is required to define the magnitude of these other loads. Okay, then add this. Okay, so now this wall load has come into this particular table. Okay, so the definition of the load is over. Then we'll assign the load. Now, how to assign the load? First of all, select the element. First of all, select the element. After selecting the element, then here the main command, assign. It is assign. Then it is a frame load. Beam is a part of the frame. So it is a frame load and it is a distributed. We'll apply a load which is a uniformly distributed load. Yes. Then here load pattern first. Okay, so first of all, load pattern will be, now select here, it is a wall load. So wall load has come here because already it is defined in the load pattern. Once it is defined in the load pattern, automatically it will create here. It will come here. Okay, so this is the wall load. It is applied in the global direction. Okay, and to define the uniformly distributed load, use this window, uniformly distributed load. And these windows are to be used for uniformly varying loads, maybe in the form of triangle, maybe in the form of trapezoidal, and so on. So this is for uniform varying loads. This is for uniformly distributed load. Okay, now substitute define the magnitude, intensity of the loading as a 20 kilonewton per meter. then apply and OK. Apply OK. Now the load has been defined. This part is over. Now next is analysis. Okay, so under this wall load, we'll see what is the bending moment and shear force diagram, how to see the diagrams. Then this is the command for the run analysis. So you just click here. Okay. Now, so these are the three cases generated are ready for the analysis. So out of the three cases, remember, first two cases, that is dead load case and model load case, the SAP 2000 automatically creates for the analysis. It automatically develops for the analysis. So therefore, user need not necessarily to create these two dead load and model load case for the analysis. Okay, so then third load case. Okay, so this is we have generated. Okay, this is generated in the load pattern, and when it is included in the when it is generated in the load pattern, automatically this load case creates here automatically for the analysis. Okay. Now we are interested to see the results only due to wall load. We don't right now we don't require the results of a dead load and model load. So we don't will not run this particular case. Okay, so just select this and here just click this button. So it will be in the action, it is do not run. Give the instruction as a this is also do not run. Only will run the wall load. Then run analysis. Then save the model. Okay, so analysis is going on. Okay, now, so this is deformed shape. So this is deformed shape. Here it is said, this is deformed shape under wall load. Okay, now we'll see the bending moment diagram. Now we'll see the bending moment diagram. Now it is so to see all the results, internal forces or bending moment shear force diagram, the command is display. Okay, so display show forces. Display show forces stresses and see frames cable tendons. Okay, now this is a window. Okay, so this is the window. Okay, now ensure that here must be wall load. Okay, now here to see the bending moment. Okay, to see the bending moment, this is bending moment 22 is there and moment 33 is there. Similarly, to see the shear force diagram, there are two, shear 22 and shear 33. Now, which for moment and shear, whether 22 to be referred or 33 to be referred, that is a question. Okay, now just see here, this is a beam. So for that, we must know what are the local axis of the beam. What are the axis of the beam in SAP 2000? Now, the local axis for the beam is, the local axis are, first is the axis 1. Axis 1 is always acting along the longitudinal direction. So to see the axial forces, axial deformation in the beam, refer axis 1. Next, now axis 2 for the beam is perpendicular to this longitudinal axis. This is axis 2. Axis 2. So therefore, the shear force diagram. Okay, to get a shear force diagram, refer shear 22. We'll get a shear force diagram for the beam. Okay, and third is whatever the bending is there. So bending, whatever we are seeing here, this bending is, it is like this. So this bending is with respect to axis 33. So 33 axis is perpendicular to this plane of the screen, perpendicular to the screen. So therefore, this deformation, whatever this deformation is with respect to axis 33. So therefore, to get a bending moment diagram, so see, click on moment 33. Okay, so just I will repeat, for the beam, to get a shear force diagram, refer shear 22, and to get a bending moment diagram, see moment 33. Okay. Now, first of all, we'll see the bending moment diagram. So click on M33, and here the option is only the diagram is required or diagram with value. So we require diagram with value. So therefore, choose this option with value, apply and OK. Apply and OK. So this is a bending moment diagram. So what is our case? Simply supported beam subjected to uniform distributed load of 20. So bending moment diagram will be a parabolic. Middle ordinate is WL square by 8. The answer is coming 90. So it is correct. Okay, so only thing is that in SAP 2000, bending moment diagram is plotted on the tension side. So therefore, the diagram we are seeing at a below the longitudinal axis. Then also we'll see the shear force diagram. So display, show forces, and here to see the shear force diagram, shear 2 Okay, so apply and OK. And now this is a shear force diagram. It is correct. So for this simply supported beam subjected to UDL at center, shear will be 0. Here it will be 60. Here it will be 60. So this is the shear force diagram. So in this way, the bending moment and shear force diagram or analysis result is to be seen for all types of the loading, all types of the loading, as well as all types of the supports. Okay. Now we'll take the another example that just will change the type of the support. Now it is simply supported beam. We'll keep the loadings the same. Only we'll change the support. Then which are the commands? So to this thing change the support. First of all, select the end nodes, end joints. First of all, select it. After selection of the two supports, then assign, then joint, assign joint, and here is the restraint. Assign joint, and here is the restraint. So these are the different types of the support we can assign in this software. So first we will provide the fixed support. We'll provide the fixed support at both the ends. So fixed support in the sense 3 translation and 3 rotations are restrained. Okay, so just click on the figure. But with this fixed support, you just click on the figure and then apply and OK. Apply OK. Okay, so load is already applied. Okay, and just we have changed the supports. Then what are the bending moment and shear force diagram? Okay, now this is the shear force diagram. Okay, so this is the shear force diagram. Shear 2. So shear force diagram will be same as the simply supported beam. Okay, so then what is the bending moment diagram? No, but bending moment diagram will be changed because there is a ends are the fixed supports. Okay, now the bending moment with respect to 3 because it is a beam. Apply OK. Yes. So this is the bending moment diagram. So is it correct? Yes, it is correct. Because at the these are the fixed supports. Okay, so fixed beam subjected to UDL. The end moments are hogging nature. It is WL square by 12. So answer is 60. WL square by 12, answer is 60. And at the center, it is the sagging bending moment, which is 30. Okay, and these are the 2 point of contraforce. So since the loading is symmetrical, so therefore bending moment diagram is also symmetrical. Okay, so this is a single span. So we can apply a different types of the loadings also. Okay, so the different kinds of the loading, different types of the loading, that is uniform distributed load, how to apply that just now we have seen. Now how to apply the point load, then how to apply the uniformly varying load, that also we'll see. Okay, so for that we'll take another beam, which is a continuous beam. Okay, so we'll take the next model, another model. So for that, let me take the new template. Okay, now here, so this is a beam, this is a beam. Now we take the span of the beam is equals to 3. Number of spans are 3, and the span length is equals to 6 meters. Okay, again the beam properties, material property as well as the dimensional property, let it be whatever the default values. Say okay. Again, one window is sufficient. Okay, now these are the 3 spans are there. Okay, now we'll do the modification in the given template. First of all, whatever A support, we'll change the A support. Now it is hinge support. Now we'll change it to say fixed support. So again here, assign joint restraint. It is a fixed support. Apply OK. Apply OK. Then now on the first span, let us apply a 2-point load. Okay, again that 2-point load will call as the wall load. Okay, it is called as, say, we'll give one name, it is a wall load. Then first of all define the load pattern. So first of all define, then load pattern. So by default dead load is there, dead load by default is there. Now we'll define the wall load. Okay, so it is a wall load. So it is a wall load is a super dead load type, and self-weight multiplier equal to 0. So add this. Okay, just will apply on this beam only one type of the load, that is a wall load. Okay. Okay, now we will apply this wall load in the form of point load. How to apply? First of all, select the beam, select the first span AB, then go here, assign, it is a frame load, right? It is a, because beam is a frame element of the frame, it is a frame load, and it is not distributed. Now it is a point load. Okay, it is a point load. Now then load pattern. So we'll apply the point load whose name is equals to, say, wall load, right? Wall load. Okay, now to apply the point load, we have to fill the information here. Okay, so these are the relative distances. So first a relative distance, that is first point. First point is this, and so this is a first point, and this is the fourth point. So that is, the span is divided into 4 parts. So define the relative distance. First is relative distance 0, that means this point. Okay, then second is relative distance equal to 0.25, that is somewhere here. Okay, so 0.25, let the magnitude of the point load is equal to 20. Okay, 20. Then third point, which is somewhere here, third point. Okay, so it is a, so at that point, let me apply a point load equals to 30. And point number 4 is here. Okay, for the newcomers, again I will, for the beginners I will explain. This is a span, this is a B. Okay, so this is a, first is relative distance 0. Relative distance 0 means this point. Okay, then relative distance 25, that is, this is divided into equal parts. Okay, so this is 0.25. This is a 0.25. This is 0.75. This is 0.75. And this is 1. Okay, now at 0.25, we have applied the load equals to 20. And here we have applied the load equals to 30. Also, now whatever these values, relative distance, these are editable. These values are editable. So therefore we can also define the, we can also change the distance as per our, if the example is there with us. So we can make the changes also here. Okay. Now, so this is a loads we have, then apply and okay. Apply okay. Okay, now these are the loads we apply. This is at a distance equal to 0.25 of the total span. Okay, this is 30 kilonewton at a 0.75. These are the 2 point loads on the first span. Okay, then on the second span, we will apply a uniformly varying load, but in the form of triangle. That is, in the form of triangle, we will apply the load like this. Okay, and this intensity is equals to 30. Okay, then how to apply this? Select the beam, then assign. Again, it is frame load, and it is uniformly varying load. It falls under distributed type. Okay, so it is a distributed. So ensure that here must be a wall load. Okay, and then this window is for uniformly varying load. Okay, so this value must be equal to 0 now. This value must be equal to 0 because we are not applying uniform varying load. Okay, right. Now these are the windows for uniformly varying load. Okay, again, so this is a relative distance 0, second point, third point, fourth point. That is, total span is again divided into the number of segments. Okay, so this is a 0, this is 0.25, this is 0.75, and this is 1. Okay, now these we can edit. Okay, so this is a 0 and this is a 1. Okay, we can change this also, that is 0.2, 0.4. So whatever our this thing distances we required, we can this. Now right now we'll keep this as a 0.25 and this is as a 0.75. Okay, then but in this particular type of the loading, that is we are applying a we are applying a triangle load, that is intensity is maximum at the center here. Okay, so what is this point is 0.5. So therefore point number 2 is a 0.5. It is a 0.5, right? And point number 3 is also a 0.5. Point number 3 is also 0.5. Okay, and what is the intensity there? It is a 20. It is 20. And point number 1, that is point number 4 is here. So what is intensity? 0. Okay, it is equals to 0. Okay, and then say apply. Okay, then here uniform load must be 0. So it is apply and okay. Okay, now it is a uniformly varying load in the form of a triangle. This is a form number 2. Okay. Then on the third span, we will apply a trapezoidal load, which is again a type of uniformly varying load. So select a span, then assign. It is a frame load, assign frame load, distributed type. Okay, so here make the change. So at relative distance equal to 0, load will be 0. At relative distance equal to say 0.25, okay, so loading will be 20. At relative distance equal to 0.75, say, then it is again 20, right? And point number 4, relative distance 1, so intensity will be equal to 0. So apply and okay. So this is uniform varying load. So on all the three spans, we have applied the wall type of load. Okay, but on the first span, it is not seen. Okay, just it is hide, but the load is there, and that load also we can see how to see that load assignment. So here go for display, and here the third, that is the fourth one, show object load analysis. So show object load analysis, and this is on a frame. Okay, so what type of load? Actually wall load. We want to see the wall load, whether it is applied or not. To check this, select a wall load, then apply and okay. Okay, so it is there. So on a beam, wall type of load is applied. So these are the 2-point loads, then in the form of triangle, in the form of trapezoidal. Okay, then do the analysis. So again, we are not interested in the first load case, dead load case. Okay, only we will see the result for the this thing, wall load. Okay, again save the model because we have changed the template. Okay, what is this? It is a bending moment diagram. It is a bending moment diagram for the wall load. Okay, so since A support is the fixed support, so therefore there is a negative bending moment. Okay, and this is a simple support, therefore the moment is equals to 0, and over the support there will be a negative bending moment. So these are the negative values. So this is about the bending moment diagram. Then next is about the shear force diagram. So display, show forces, frames, and then shear to two. Then apply and OK. Apply and OK. So this is the variation of the shear force along the span. So since it is uniform by varying load, so shear force diagram will be a curve.